In this video, we're going to take a look at vectors in kinematics. So vectors can be used to describe motion in a plane. And let's say we have a particle that starts from the point with position vector r0 and it moves with constant velocity v. Then the displacement from its initial position at time t is vt, and the position vector r is given as follows. So r here, this is our position vector at time t. That is equal to r0. So this here is our initial position vector. So that's the position vector at time t equals 0. And then we have plus vt. Okay. So just a quick point here on the notation, just in case you aren't familiar with this notation. So the lines here underneath these letters, these represent vectors. So we have a line here, here, and here. But we don't need a line for t because time is a scalar rather than a vector. Okay, so just so you're familiar with that notation that we're going to be using throughout this video and the next few videos in this chapter. So this result here, like we said, this is for constant velocity. Okay, so let me just make a note of that here. So this result is for constant velocity. So if this is for constant velocity, this result, so this is for constant velocity, what about when we're working with constant acceleration? So cast your mind back to the first year of study and when we were working through SUVAT problems, okay? And you might remember the equations of motion or the SUVAT equations, okay? And the question here is then, do we have a vector equivalent for these SUVAT equations? And the answer to that is yes, we do. So let me just recall the vector or the SUVAT equations here. So I have v equals u plus at. Okay, so that's our first result there. And then the second result that we're going to use here is r equals, so I have r equals ut plus a half at squared. Now, this second result here might look a little bit different. So the reason why that might look a little bit different is because normally it's s equals ut plus a half at squared. However, when we're now working with vectors and kinematics here, rather than using s, we do prefer to use r. Now, these are the two results here that you should hopefully be familiar with from the first year of study. So these are the SUVAT equations of motion. And because we're now working with vectors here, obviously I need to make sure that I've got my lines underneath here to represent the vectors. So I've got v here, so that's a vector. U is also a vector here, and A is a vector again. Obviously t, like we said, is a scalar, so we don't need a line under that. And same again here for the second equation of motion. So R is a vector, U is a vector, and A is a vector. Now, we do have more equations of motion, like you might remember from the first year of study, but for this chapter here, we're mainly going to be concerned about these two results here. Okay, so these two results here, what we're particularly concerned with. Okay, and these two results are when we're working with constant acceleration. Okay, so constant acceleration there. So other than that, the only point to really kind of finish with here then is you can either give these vectors in IJ notation or you can present the vectors as column vectors. This is a preference thing and it's completely up to you. I personally prefer IJ notation, so I'm going to stick with that throughout these videos. However, if you do prefer working with column vectors, then that's absolutely fine. But like I said, it's a preference thing and it's completely up to you. So I think that covers everything then that we need here for our introduction then to vectors in kinematics. What we're going to do now is just take a look at a couple of practice questions for vectors in kinematics. Starting off with question 1 here then, where we have a particle that starts from the point with position vector 4i plus 2j meters, and it moves with constant velocity of minus I plus 2j meters per second. So for part A here, I want to find the position vector of the particle after 6 seconds. Now, the first thing that I noticed with this question here is that we're working with constant velocity. Okay. So because we're working with constant velocity here, we need to make sure that we're using the correct result. So for part A then, because we're looking for a position vector after a given amount of time, we're going to use R here. So my position vector at time t is equal to R0, this is the initial position vector, plus Vt. Okay. So in terms of this question here, the information that we have I've got my initial position vector here. So that's r0. We've also got v here, so my velocity vector. And then t here is given in part A. So that's t. Okay. We've actually got everything that we need then to answer part A. So if I just substitute in everything appropriately here, I get that r is equal, so r0, that is 4i plus 2j. So 4i plus 2j plus vt. So my velocity vector here is minus I plus 2j. And then we times that by t here, which is 6. I've got 6 lots of minus I plus 2j. Okay, like so. So now what I need to do here is just collect the I components and the j components here. So I've got 4 plus 6 lots of minus 1. So that's the same as 4 minus 6, giving me minus 2 there. So r here is equal to minus 2i. So minus 2i. And then for the j component here, I've got 2 plus 6 lots of 2. So 2 plus 12, giving me 14 there. So plus 14j. And this is a position vector, so meters here. So this would also be meters as well. Okay. So there we have it. So that's the solution there to part A. Hopefully nice and straightforward just to get us started. And then for part B here, it says find the time at which the position vector is due north of the origin. So if you just think about this problem for a moment, when my position vector here is due north of the origin, that would mean the actual I coefficient here is equal to 0. Okay, if it's due north, we're traveling in that direction here. So due north. And like I said, that would mean then that the I coefficient is equal to 0. Okay. So in that case then, let's just go back to our position vector. So again, we're going to use this result here. So use r being equal to r0 plus vt. Okay. So r0 here, again, that will be the same. So that's 4i plus 2j. So that's 4i plus 2j. 4i plus 2j. Now I've got vt here. So t, we don't know what that is. That's what we're looking to solve for. So I've got t lots then of my velocity vector here, which is minus I plus 2j. So plus minus I plus 2j. And I've got t lots of this. Okay, so I'll put the t at the end here, like so. And now what I want to do here is collect the I components together and the j components together. And then once I've done that, I can then set the I coefficient equal to 0. Okay, so in that case then, r here, well, I've got 4i and then I've got minus I times t here. So in terms of the actual I component here, this is going to be 4 minus t here. It's minus 1 times t. So I've got 4 minus t here. That's my I component. So hopefully that makes sense how we've done that. Doing the same then for the j component here, I've got 2j plus 2j, but don't forget this is times by t here. So in this bracket, I get 2 plus 2t. And that's for the j component there. And then like we said, the coefficient here of my I component here then, so this coefficient here must be equal to 0. Okay, so let me just make a note of this in red. So this part here must be equal to 0 because it's due north. Okay, so because it's due north here, this part will be equal to 0. So all I need to do here then is just solve this part then for 0. Do that up here. I can see then that 4 minus t is equal to 0. And therefore, t is equal to 4. Okay, so that's 4 seconds there. And there we have it. So the time at which the position vector is due north of the origin is 4 seconds. That gives the solution to B and the solution to question 1. Taking a look then at one more question here where we have a particle that's moving with constant acceleration such that its velocity changes from 3i plus 4j meters per second to 6i minus 2j meters per second in 3 seconds. So here I want to find, to begin with, the acceleration of the particle. So for part A then, looking for the acceleration of the particle, the first thing that I notice with this question is this phrase here of constant acceleration. So straight away, this suggests to me that we need to use the equations of motion, or in other words, the vector equivalent of our SUVAT equations. Okay, so make a note of that here. So we're using SUVAT. So if we're using SUVAT here, I think a good place to start is just to define the information that we already have. So rather than using S here, I'm going to use R. We just prefer to use R rather than S. So R, U, V, A, and then finally T here. So we have no information that pertains to R, so we'll leave that blank. For U then, so that's the initial velocity here. So that would be 3I plus 4J. We've got 3I plus 4J there. For V, that's our final velocity, or our velocity at time t. So that would be 6I minus 2J. So 6I minus 2J there. For A, we don't know what that is. That's what we're looking to solve here for part A. So I'm going to put a question mark there, just to indicate that that's what we're looking to solve for. And then finally T here, the time, well, that would be 3 seconds. Okay, so T equals 3 there. So that's all the information that we already have here. So we're using the SUVAT equations here, or the vector equivalent of those SUVAT equations. And like we said, there's only two that we're actually particularly interested in here. So it's either going to be V equals U plus AT, or it's going to be R equals UT plus a half AT squared. And based on that fact and the information that we already have here, we're going to use V equals U plus AT. So use V equals U plus AT. So just marking my vectors here. So what information do we already have? Well, we've got V here, so that's 6I minus 2J. So 6I minus 2J. This is equal to U, which is 3I plus 4J. So 3I plus 4J there. And we then have plus AT here. So A, we don't know what that is, but we know that T is equal to 3. So I get plus 3A there. Like so. So now what I need to do here is collect the I components and the J components on one side. So I'm going to subtract 3I and 4J off both sides here. In that case then, we get that 3A is equal to 6I minus 3I, so it would be 3I there. We've then got minus 2J minus 4J, so that gives me minus 6J there. And then finally, if I just want A on its own here, I'm going to divide both sides by 3. So 3I divided by 3 would give me I. And then minus 6J divided by 3, that would give me minus 2J. Okay. And don't forget the units here. So for velocity, it was meters per second. In that case, then for acceleration, this would be meters per second. So ms to the minus 2 there. Okay. So there we have it. So that's the solution to part A. So what about part B then? Let me just kind of split this off a little bit here. So for part B then, okay. So this is part A and this was part A here. So for part B then, if I do this in this kind of bottom right area here, we're now looking to find the speed of the particle when t equals 5. So the first thing to note here is if we're looking for the speed, you need to remember that the speed is the magnitude of the velocity vector in this case. Okay, because we're now working with vectors in kinematics. So not only would you say that speed is the magnitude of the velocity, because we're working with vectors here, it's the magnitude of the velocity vector. But this doesn't change anything, so the method is the exact same. It's just simply Pythagoras on the velocity vector. But we need to get to that point first. So again, we're going to use V equals U plus AT, because what I need is the velocity at t equals 5. So again, we're going to use V equals U plus AT. So V is equal to U plus AT when t equals 5. Okay. So V, that's what we're looking to find. So I'm just going to leave that as it is for now. That's going to be equal then to U. So my vector here, so that's 3I plus 4J. And then we've got plus AT here. Well, A, we actually know now, so that's I minus 2j, and t in this case is 5. So what I've got here is 5 lots, so plus 5 lots of I minus 2j. Okay, so if I just simplify here then, for my velocity vector, well, I've got 3i plus 5i, so just expanding this out here. 5 times I would give me 5i, so 3i plus 5i gives me 8i there. So I get 8i there for the I component. And then what about the j components here? So I've got 4j plus 5 lots of minus 2j, so that's minus 10j plus 4j, so that would give me minus 6j there. Okay. Now be careful, that isn't the question done here, because like we said, we now need the magnitude here of this velocity vector. So let me just make a note of that here. So speed is equal to the magnitude here of my velocity vector. Okay. So I now need to find the magnitude of this velocity vector here. So therefore, speed is equal to the magnitude here of b. And that, like we said, that's simply an application of Pythagoras. So it's going to be the square root of 8 squared plus minus 6 squared. So 8 squared plus minus 6 squared. So if I evaluate this here, that's 64 plus 36. That gives me the square root of 100. And the square root of 100 is simply 10 there. Okay. And again, don't forget the units here. So this is speed. We've been working in meters per second, so my speed will also be meters per second. Okay, so ms to the minus 1 there. Okay. And there we have it. So that's the solution to A here. That's the solution to B. And that gives the solution there to the very last question, question 2. And that brings the end of this video on vectors in kinematics.